So as we move into the notes here for 3.1, we'll see that we're going to start by trying to shape out a general idea for how we can actually use the product rule from Calc 1 to develop a useful formula for integration. So I'll start here by just quickly saying that we should be able to recall the product rule. So we'll say recall that for differentiable functions f of x and g of x, the product rule states that if I wanted to take the derivative of the function f of x multiplied to the function g of x, you might recall the following sort of setup that we had in the Calc 1 class. I would take one of those functions and leave it alone and multiply it to the derivative of the other function. I would then add and kind of reverse the order on which thing gets the derivative. And so this was our product rule. Again, it doesn't matter which one of these terms you write first, because since it's addition, the order is irrelevant. But what we're going to do is try to use this rule again to develop a rule for antiderivatives. So I'll start by saying this. Now, by using our knowledge of indefinite integrals, we can obtain the following. First off, I think it would be pretty easy to see that if I was to go ahead and attempt to integrate everything that I had over on the right-hand side of that product rule statement, if I wanted to integrate that, do you have a sense of what I would actually create? What would this be equal to? Where would this come from? Well, it's probably no surprise to see that over on this side, I would just be right back to my f of x times g of x. Of course, I might remember that when I use an indefinite integral, I always have the possibility at the back for a plus c. There could be a constant over here, and of course, when I take the derivative of this right-hand side, I'd be right back to what I have over here. Now, I'm going to go ahead and quickly see here that I can easily go ahead and separate the integral that I have up above into two integrals, right? I can kind of separate across that addition, and so I'll go ahead and do that here, and then I'll still have my f of x, g of x, and my plus c. And so now I'm going to go ahead and just imagine what it would look like if I took this second integral that I had here and I kind of just moved it over to the other side. I mean, it's an item that's being added to the left, so if I subtracted it from both sides, I should end up with an integral that looks like this, should now be equal to my f of x times my g of x minus the integral of f prime of x g of x dx. Now, it might seem at first that I've forgotten to write this constant of c that I had up in the last line. But remember that this indefinite integral is also going to produce a plus c once evaluated. And that c could really be any number, so I've kind of just rolled this value of c together with the value of c that's in here. I've kind of shoved that c inside, if you will, of this indefinite integral. If that's uncomfortable, you of course could still write the plus c, but we'll see here that it's actually a little bit better if I don't for the moment. And I imagine that c again is moved inside of this integral. Now, if I look at this, this kind of tells me that there's an interesting relationship. It says that if I was ever interested in trying to compute an integral of the following form, so an integral where I had a function multiplied to the derivative of something, then I would know that that's equal to the two original functions multiplied minus a new integral. You'll almost kind of remember this as something similar to what happens in a u substitution, in that in a u substitution you start with a complicated integral, and after your substitution you still have another integral to evaluate, but your hope is that that new integral will actually be easier than the starting one. Now, to make this a little bit more palatable to see, I'm going to go ahead here and let's just suppose that I make some initial replacements here. Okay. I'm going to go ahead and actually state, how about we let u be equal to f of x? Like everywhere I see an f of x, I'm just going to replace it with a u for simplicity. And I'm going to let v be the same thing as g of x. Well, if that's the case, then definitely I know that du is equal to f of x dx, and dv is equal to, oops, sorry, that should be f prime of x dx. And dv is equal to g prime of x dx. Now you can kind of almost see here where I can color coordinate each of these different pieces. If u is the same as f of x, then I can put a u in here and a u in here. If du is the same thing as an f prime of x dx, then I can put a du over here. I have my g of x component, which can be replaced with my v. And then notice that I have this other component, and I'll have to use a different color here, but I have my other component, this g prime of x dx, which is listed right here at the front. So everything's kind of accounted for, and I can replace everything that I have here. So with this in mind, I can then see what our equation turns into. So I'll say our equation becomes an integral, notice, of u multiplied by dv, and that should be equal to u times v minus an integral of, over here, notice I actually forgot to mark, there's another instance of v, and then I'll write all the green stuff at the back, which is du. And so oftentimes, this formula right here is the formula that we'll remember as our integration by parts formula. In fact, I'm going to go ahead and just copy that down one more time in the box below. Remember, what this integral is really showing us is that if I ever had something in the following form, if I had something I could call u multiplied to a dv, that's equivalent to writing u times v minus an integral of v du. Or sometimes people over here at the back can remember that by just remembering voodoo. I've often heard that. So that might be something to help you kind of remember the order of this. It's very important that we do know what the order of this is in order to be able to apply this to some specific examples. And in the next couple of videos, we'll take a look at a lot of different examples to see how we can use this idea to integrate things that otherwise in Calc 1 would have been impossible to integrate.